Hi, this is John Isles and welcome to Geometer's Paradise. Today we're going to be talking about Unit 6, Lesson 1, the classification of triangles. We have two goals here. First, that students will be able to classify triangles by their angles as either acute, obtuse, or right, also equiangular. Students will also be able to classify triangles by their sides, scalene, isosceles, or equilateral. We're also going to look at a couple of proofs that show that obtuse triangles and right triangles can only have one side or one angle that is obtuse or right. Okay, so the first thing we want to talk about is what is a polygon. The shapes on the left are all polygons, which is a special kind of geometric shape that has the following rules. Number one, they have to be straight line segments. All the sides are segments. Okay, number two, each vertex connects two sides. And number three, the shape must be closed. Okay, so if you look over here, each of these pictures violates one of these two rules. The first one violates rule number one because it's a curve. All right, this is a circle. There are no line segments. It's just a curve. You can also have something that looks like this, okay, where there's a semicircle on the end of it. Okay, and then this would be not a polygon either. The problem with this shape is right here. This vertex connects four sides. Okay, this is a problem. This shape on the left is a polygon, and the shape on the right is separately a polygon, but the shape taken as a whole is not a polygon because this vertex connects four sides. And this one is open. Okay, this is not a closed shape. The end is open here. Okay, so what kind of shape is a triangle then? Well, a triangle is a polygon. Specifically, it's a polygon that has three sides. We usually classify our polygons by the number of sides they have. This polygon has three sides, so it's a triangle. You'll notice that every polygon has the same number of angles as it has sides. Here this has three sides and this has three angles. Now you might say, hey, wait a minute, Mr. Isles, what about the star here? This is a polygon. Does it have the same number? Whoops. Does it have the same number of sides as it does angles? Well, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. Now we have 1, 2, 3, 4, 5 angles in the interior. But we also have 1, 2, 3, 4, 5 angles in the exterior, which is a total of 10 angles and 10 sides. So even though this shape doesn't have all of the angles on the inside, it still has 5 angles on the outside and 5 on the inside and 10 total sides. Okay, something to keep in mind here that we haven't really discussed yet is that this shape is what is called concave, where this shape is called convex. Okay, a concave shape is one that passes, if you extend the side, it passes through the interior. Okay, if I extend sides here, they do not pass through the interior. Okay, so that's the difference between concave and convex. Okay, so when we classify triangles by their sides, we're asking if 0 sides are congruent, if 2 sides are congruent, if 3 sides are congruent. If 0 sides are congruent, we call the triangle scalene. If 2 sides are congruent, we call it isosceles. If 3 sides are congruent, we call it equilateral. But there's an interesting property for equilateral triangles. An equilateral triangle is also isosceles, because if you have 3 congruent sides, then you certainly have 2. We mark congruence using little hash marks on the triangles. So for example, this would indicate that these two sides are congruent, whereas this would indicate that these three sides are congruent. Now when I say that an equilateral triangle is also isosceles, I mean to say that if I take these two sides together, that's two congruent sides, which satisfies the condition for isosceles. The other thing we want to talk about here is the way that we mark up these triangles. For example, if I were to mark this side here as a 2, this means that this side and all three of these sides are the same length, while these two sides are also the same length. Okay. So, we want to classify triangles by their angles, and we usually call them acute, right, or obtuse based on whether or not they have the angle of that name. In order to do this, what we do is we draw perpendicular lines. So if I draw a line perpendicular to the corners, okay, as best I can. That one wasn't very good. Okay, we draw these perpendicular lines, and if the angle fits inside of the perpendicular line, it's acute. This angle is an acute angle. This angle is an acute angle. But if I try to draw that perpendicular and it sits on the side like this would if I had drawn it exact, then I can tell that this angle is a right angle based on that perpendicular line. So we call this triangle then a right triangle because it contains a right angle. Now look at the drawing on the right here. It should be pretty clear that both of these sides contain acute angles. But if I draw the perpendicular to this side, the perpendicular line actually goes through the center of the triangle. I'm going to try that again. Okay, so see the perpendicular line passes into the interior. This is the right angle, and that makes this angle up here obtuse, which makes this triangle an obtuse triangle. So we have acute angles on the wings, and we have an obtuse angle here at the top. If I try this trick down here on this triangle, that was really bad. It goes like this. There we are. Okay, see each of these right angles contains an angle. So each of the angles fits inside of a right angle. So we call this triangle acute. All right. So the question we ask ourselves for classification by angles is, are any of the angles greater than 90 degrees? Sorry about that again. Okay, so first in the first case, we say, okay, hey, this angle is 90 degrees, so we call it a right triangle. Or in this second case, I might say that this top angle is greater than 90 degrees, so we might call it an obtuse triangle. Or on this bottom one, none of the angles are greater than or equal to 90, so we call it an acute triangle. But an acute triangle also has a special case. If all the angles are equal, then the classification is equiangular as well as acute. Okay, as an example, here we have a triangle where AB is equal to BC. So that means that these two segments are congruent to one another. That allows us to classify this triangle as isosceles, which in turn allows us to set it up in equation, or 5x minus 2 equals 3x plus 12. This is because we have an isosceles triangle. Remember, in geometry, we have to validate everything we write. So here we say, okay, it's an isosceles triangle, we can set them equal. Subtract 3x from both sides, we get 2x. Add 2 to both sides, we get 14. Divide both sides by 2, we get 7. So that satisfies this question. But what if the question also asked us to compute the length of AB? We would have to take our 7 and plug it back in. So if I put 7 in for x, I get 35 minus 2, which is 33. I can do the same thing over here. 3 times 7 is 21, plus 12, 33. Okay, we want to classify the triangles based on their angles, ABC. Here's triangle ABC, which contains a right angle, so ABC is a right triangle. ACD also contains a right angle because AC is perpendicular to BD, so both of these angles are right angles, which means ACD is a right angle, so ACD is a right triangle. ABD, this large triangle, is called obtuse. It's an obtuse triangle because 70 plus 30 is 100 degrees. So this angle is obtuse. Triangle CED is this small one here. And we know that this angle is a right angle, which means that ECD fits inside the right angle, which makes this an acute triangle. All right, and then you might say, hey, that makes this acute too, right? Well, it's true that this angle is acute, but this angle is not, because it's a linear pair. And a linear pair always contains an acute angle and an obtuse angle. The measure of this obtuse angle is 110 degrees, not the 40 that I just wrote. Let me fix that. 110. So ACE is an obtuse triangle. All right, so let's get a little proofy now. The first thing we want to talk about is something called proof by contradiction. A proof by contradiction works with on and off type statements. We can prove that a statement is true by proving that the alternative of the statement is false. And this is true anytime we have this kind of on-off type situation. A right triangle is one that has exactly one right angle. So this is a true statement. Right triangles have exactly one right triangle. So the assumption here is that all the angles of a triangle is greater than 0, and this is also true. So what if we let there be two right angles? Let's suppose that A is a right angle and that C is a right angle. Okay? So that means that, and I'm going to go with the degree system, that means that angle A is equal to 90 degrees and that angle C is equal to 90 degrees. So the third angle, okay, 180 minus 90 is 0 degrees. That means this angle must be 0 degrees. Okay, this is a problem. It's called a contradiction. Because in order to be an angle, you have to have a measure greater than 0 degrees. But if a triangle has two right angles, that means that one of its angles has to be 0, and it can't be. So this is a contradiction, meaning that there can't be two right angles, there must be just one. We can do the same thing for an obtuse triangle. All right, the way this works is we assume that there are two, and we pick them. We say, okay, how about CB1 and BB1? So generally, this means that angle C is greater than 90, and that angle B is greater than 90. All right, we can add these two inequalities together. This means that angle C plus angle B is greater than 180 degrees. So if C plus B is greater than 180, what does that mean for angle A? Well, it means that angle A is less than 0. Because C plus B is greater than 180, and A plus C plus B is supposed to be equal to 180. That means angle A is negative. This is also a contradiction. Okay, again, because all the angles of a triangle is supposed to be bigger than 0. Okay, an equiangular triangle is one that has three congruent angles. They all measure 60 degrees. So how do we know that? Okay, well, all of these angles are equal to one another. So let's call this x. Then the measure of this is x, and the measure of this is x. Okay, So we also know that the angles of a triangle sum to 180 degrees. We proved this theorem in the last chapter at the very end. So if I just write in an x for each of these measurements, then 3x is equal to 180 and x is equal to 60 degrees.